Welcome to the APL quest. See APL Wiki for details. Today's quest is problem 6 from the 2015 round of the APL problem solving competition. We're given two rectangles as two coordinate pairs, and we have to check if they overlap. And that can be a little bit hard to think of just in terms of words. So let's illustrate it. Here are two rectangles. And we can label their corners in order not to get confused which rectangle we're talking about. We're not just going to use x and y like we normally would, but we're going to use an alternately named coordinate system for one of them, where the horizontal axis is A and the vertical axis is B. So we got the XY rectangle and the AB rectangle. And we can see here that each one of the elements in the coordinates are defining an edge. So the left edge of the XY rectangle is defined by the x1 coordinate, and the bottom edge is defined by y1. Similarly, A1 defines the left edge of the other rectangle, and B1 the bottom edge. Now we don't know what order these are given in, and that's something we have to keep in mind. But for simplicity, just keep it like this. And here we can see that the vertical edge, left edge of the xy rectangle, which is defined by the x-coordinate x1, and the vertical edge, the right edge, defined by x2, fall in between, so to say, the range between the vertical edge of A1 and the vertical edge of A2. And similarly, but oppositely, the edges defined by B1 and B2 fall in between the edges defined by y1 and y2. And clearly, these two rectangles overlap. Now, when AB is entirely contained, we have still the edges, even though they don't intersect, the edges A1 and A2 are in between x1 and x2. B1, B2 are in between y1 and y2. And even though there's only a partial overlap like this, we still have at least one edge vertically, x2, between A1 and A2. And both of the horizontal edges, B1 and B2, are in between y1 and y2. Now there's only one of each. So the edges x2 and y2 are in between the corresponding vertical and horizontal edges on the other rectangle, but also A1 and B1 are in between. And here we have both x1 and x2 in between, and only B1 in between the other, and then y2 in between B1 and B2. Now there's no overlap anymore. Even though x1 and x2 didn't move, and they're still in between A1 and A2, it isn't the case anymore that any of y1 and y2 are between B1 and B2. So we can see that in order for there to be an overlap, there must be at least one horizontal edge that is of one rectangle between the horizontal edges of the other rectangle, whichever one it is. And there has to be at least one vertical edge from one rectangle between the two vertical edges from the others. Of course, if you move the rectangles entirely away so that nothing is in between each other, then there's no overlap either. Here there is an overlap vertically, in that B1 is between y1 and y2, but there's no horizontal overlap because both A1 and A2 are on the same side of x1 and x2. And so, while close, there is no overlap here. Both conditions have to be held. And we're going to use this as our case where it is false, there's no overlap. Moving x1 and moving the xy rectangle a little bit to the left, there will be an overlap just in the corner, and we can see that we have the edges x1, and y2 in between the corresponding edges on the other rectangle, and also, of course, follows with that B1 and A2 are in between the corresponding edges of the XY rectangle. In the code, we're going to use labels for these. It's the same rectangle, AB, but we'll have XY1 and XY0 for the one that should give true and the one that should give false. And then, in order to give them some concrete values that we can work with, let's just set an origin point, which is where the A1, where the B1 and the X1 edges would meet had they continued out. That gives us some nice small positive numbers to work with, but this of course will be very general. Right, so AB will have 0, 2 and 5, 9. XY1 for 0, 11, 3. XY0, 8, 0 and 13, 3. And now we'll start building things up. So let's just make a placeholder function for now, the concatenation of the enclosures that just juxtapose the two arguments. And we're going to run our test cases every time. So we have AB with XY1, and then let's output a little line and do AB with XY0. So this gives us our arguments. So these are simply A1 and B1, A2, B2, X1, Y1, X2, B, Y2, and the same thing at the bottom. This encapsulates A and B values together and X and Y values together, and we really want to consider them separately because the condition is that there separately are overlaps horizontally and vertically. So the first thing we're going to do is we're going to mix these to get nice matrices to work with, and then but we still have each row being a mixture of horizontal and vertical values. We can fix that by transposing. Now that we have transposed, we have A1, A2, X1, X2, B1, B2, and Y1, Y2. And we can start working on these. And so what exactly was it that was our condition? We're going to work on each row separately. So let's use rank 1. And then we're going to start stating what exactly is it we're looking for. So for each row, that means we're considering the horizontal component and the vertical component, and they're being run separately because of the rank 1. So we can just talk about 1. Let's talk about the horizontal component. That's the X1, X2, A1, and A2. On the left, we have A1, A2. On the right, we have Y1, Y2. So the lowest one on the left, because remember, we don't know what the order is going to be, so we can't just say it should be the first one, which would, in our case is A1 and is the lowest one, but maybe it's A2 that's the smallest value. So we take the smallest one of those. So the smallest one of A1 and A2 has to be less than the greatest one of the corresponding on the right, which is X1 and X2. So if the smallest one on the left is below the greatest one on the right, then they might overlap, but that's not sufficient, because we also that they could both of them, both A1 and A2 could be below X1 and X2. So we have to have an additional condition, which is that the lowest one on the right, so that's the lowest one of X1 and X2, also has to be less than the highest one of A1 and A2. So now we know that they overlap in this component. And since we're doing this for each row in our matrices, we're doing this separately for the horizontal part and the vertical part. And then the only thing we need to know then is it both true? Is there an overlap horizontally? Is there an overlap vertically. So if both of these are true, then there's an overlap. And we can see here that the xy1 case gave us a 1, and the xy0 case gave us a 0, which is exactly what we'd expect. So this is one solution. But we can clean it up a bit. Because think about it. We're doing things rank 1 on each row after we transpose. So if we don't transpose, then we need to do things on each column instead. And we can't do that with the rank operator, but we don't need to, because each doing things down, so that's a reduction vertically, we can do that with reduce first instead. So that's one simplification. Another thing we can see is that there's a very strong symmetry here. The component on the right of the inner end and the component on the left of the inner end in this fork are pretty much identical, except one thing. This points to the right, this points to the left, this points to the left, and this points to the right. So they're doing the same thing, but they're swapping their arguments. And so if we give a name to this inner component, then on the left, we can just use it with swapped arguments. And we can even get rid of these parentheses here. So this is a very nice solution to the problem. Let's go for an entirely different one. This time we'll start writing a different. And again, we'll just start off by juxtaposing the arguments. Oops. Of course, we need to put G over here as well. There we go. Okay, so here are our arguments again. And instead of doing this whole mixing thing, now we're just going to use an outer product, because we want to compare all these values and see which ones are below each other. So this is an outer product between the pairs of A1, B1 with X1 and Y1. So this is saying, so for each one of these comparisons, we get these two values, one for the horizontal component, one for the vertical component. So this is saying that A1 is less than X1 and B1 is not less than Y1. And this is saying that A1 is less than X2 and B1 is also less than Y2. And then we go on to the next AB coordinate, so that's A2 is not less than X1 and B2 is not less than Y1. And finally, A2 is less than X2 and B2 is not less than Y2. Phew. Okay. Now, remember that we want edges to be in between the edges from the other rectangle, but it could be any of them. So since less than shows whether or not we are on the left or below, and so we need to have we need to have at least one edge for each that is below and one that is above some other edge in the same along the same dimension from the other one. Then the only thing we need to know really is if they're different. We don't care which one it is. We just need to know that one is less and one isn't less than. So by applying a different from reduction, we're going to again compare element wise. So we're going to compare this element here, whether a1 is less than x1, with this element over here, which is whether a1 is less than x2, which is exactly what we want, right? If the a1 edge is the one that is the determining one that is in between the other two, then these two values would be different, which we can see it isn't here. And same thing here, we go for the vertical components, that is the one that's going to be different. And same thing here, this is a2 is different from so this is a2 versus x1 and a2 versus x2. And so being that they are different, that means that the a2 edge does fall in between there. And then we can see that it is here in the top right and in the bottom left. Those are the ones where they are different. So those are the ones that will give that cause the intersection to be there. So because this is in the right side, so this is the vertical component, this is the left side, this is the horizontal component. So this is saying that the edges that are in between are B1, which falls in between Y1 and Y2. And there's also A2, which falls in between X1 and X2. So the only thing now we need to know is whether we have at least one horizontal component and at least one vertical component that's where this is going to be true. However, and this isn't enough. We also want to know whether this happens in, well, because it doesn't have to be that it is the AB, which is in between XY. It could also be XY that's in between AB. So how would we know that? Well, we just reduce in the other direction. And then we can see if any of those are true. So we could write this as one or the other. However, we can be a little bit clever about it. They're actually the same, except we could transpose first. So we can write the leading axis one as the reduction over the transpose. And now we want to know if any of them, of the one that's transposed and not, are going to be true. So we can do all the reductions in one go. If we just concatenate along the first axis with its transpose, its own transpose, then we get this 4-row table. And so really the bottom 2 rows are the transposes of the first 2 rows. That means we can just reduce across, and then the last 2 across reductions are actually equivalent to vertical reductions. So now we can do our different from reduction across to see if there is a different relationship to the edges on the side. And once that's done, we just need to know whether there is at least one vertical, at least one horizontal component where this is true. So we can mix it all, and then so the left side here are all the horizontal ones, and the right side is all the vertical ones, which means we can get whether any is true with a vertical reduction. And then we just need to know whether both of them are true. And that gives us the solution, which is also very nice. And finally, let's start over yet again for another approach. This time, we're not going to do the direct comparison, the outer product with less than, but we are going to start with an outer product. This time we're doing a subtraction. Why a subtraction? Because we can actually see on the sign whether or not something is less than or not. So if you get a negative value, it must be that the alpha component here was less than the omega component. And since we're not actually interested in the magnitude of their overlap, we're just interested in whether or not they're overlapping or not, we can take the sign of that. And here, this means that A1 was less than x1 and A1 was less than x2 and B1 was less than y1 and B1 was less than y2 and so on. Now we need to think a little bit. So we need to know whether there were any that were in between. In order to, let's state the opposite. Let's say that they were not in between. So if one component was, or so you say, if both horizontal components of one rectangle were on the same side of the corresponding components from the other rectangle, then all of these numbers that in that dimension would be the same. So really there are only two ways in which we don't have an overlap. And that is if we've got for each dimension 4 negative ones or 4 ones. If there's any value which is of the other sign than its companions, then that means that it has the other relationship and then it lies in between. So let's flatten that out. And then remember that the first element in each of these pairs corresponds to the same dimension. So these are all the A's and the so the A's against the X's, and there are 2 of one and 2 of the other, so that gives us all 4. And now if we sum this, then we get added all the first elements together and all the second elements together, giving us these 2. And remember that the only case where there's no overlap is if they're all the same. That means the sum has to be 4 times negative 1, meaning negative 4, or 4 times 1, meaning 4. In other words, the magnitude of the sum is 4. So if we disclose this, because we got an enclosure when we did a reduction over these pairs, and then take the absolute value of this, then only in the case when there's 4, there's no overlap. And we can see here that horizontally there's no overlap, but vertically there is an overlap. What we're interested in, of course, is that there is an overlap. So there is an overlap if the sum is different from 4. And these are the horizontal and vertical components, and we have a full proper overlap if both horizontal and vertical components are true. We just need to say that both of them are true, which we can do with an AND reduction over them. Okay, now that we have this all these different solutions, let's look at some comparison of performance here. It can be quite varied. And for that, we need some test data. And it doesn't really matter what the values are as long as we get a bunch of different values relative to each other. So and their magnitude doesn't really matter. What we're going to do is we want to to create some ABs and some XYs. And then let's make some random numbers. And so we have two variables here, the ABs and the XYs. Let's let them have 100 pairs each, where so the pairs are the two element vectors of two element vectors. So because we need the two for the for one corner, two for the other corner. So two with two in each, and with 0 here, then this would give us just some random floats between 0 and 1. But we want it all to be nested, so we'll split it. This gives us a 2 by 100 by 2 array of pairs. We split it again, now we get a 2 by 100 array of pairs. And we split it one final time, and now we get a 2-element vector of 100 element vectors of pairs. Let's copy in CMPX from defense and construct the expression that we're going to run. So this is the ABs joined up with each of the function names f, g, and h with the XYs. Let's check that this looks good. Yeah, that looks fine. And then look at the performance for that. And turns out that our initial implementation that was very much based on how we phrased the problem is significantly faster than trying to do any of these clever tricks. So that's all. Thank you for watching.